All right, so far we've got a pretty good sense of how to relate the physical properties of a gas, pressure, volume, amount, and temperature for a single gas. So if you've got a balloon and you know any one of these properties, except for one, we can solve for the other for that single gas. But what happens if inside that balloon you've got a mixture of two things or more, so helium and neon? Now, the pressure and the volume and the temperature are all still going to be independent of the fact that you've got more than one gas, but the quantity, how do we treat that? That means we're going to have multiple ends, right? So how do we equate that to what we know already of the ideal gas law? So with the multiple gases, of course, we're going to have different amounts of each or different ends. And we can think about that in our sort of balloon example in here, that the pressure inside of this balloon, the total pressure, is going to be a sum of all of the individual pressures of the different gases. In that case, that's going to be equal to the pressure of the helium plus the pressure of the neon, right? So we just need to essentially write up an ideal gas law for each one of those gases, solving for P. So what would that look like? So for the pressure of the first gas, pressure of 1, which could be the same as, say, pressure of just the helium, that's going to be the amount of that gas, N1, times the gas constant, the temperature, divided by the volume, all of which are constants in the system. They're unchanged and unfazed by the fact that there are multiple gases. We could write out the same for pressure of the second gas, N2, RT over V. In other words, we could sort of substitute these in and pull out the n's. So we have N1 plus N2 plus N3, etc., times whatever the gas constant temperature over volume term is. Where these quantities, N1 plus N2 plus N3, these are just the individual amounts of each gas in the mixture multiplied by whatever the overall RT divided by V is. To relate that back to that sort of original hypothetical example of helium and neon, the total pressure inside that balloon then is just going to be the number of moles of helium plus the number of moles of neon times whatever the temperature and the gas constant over the volume of that balloon are in that physical scenario. We call these individual pressures here P1, P2, P3, or up here more specifically P helium, P neon. We call those partial pressures. And we call them partial pressures simply because they're part of the total pressure and they add up to whatever the total pressure is. So it's pretty simple. If we know how much of each of the gases are there, we can write an ideal gas law for each, or a simplified gas law where we've pulled out the number of moles of each, and the sum of those partial pressures is always going to add up to the total pressure of the balloon. So pretty straightforward. So another convenient way, what I just walked through for partial pressures is absolutely true, but a more convenient way that's often used to express partial pressures is to use this version, or this other sort of formalism called mole fraction, which we have this x, or more accurately the Greek letter chi, so it's sort of a squiggly x. And that's going to be the moles of whatever the of one of the gases is, divided by the total moles of gas. That's the fraction of the moles that are that gas. So to keep working with this example here of helium and neon, if we wanted to figure out the mole fraction of, say, helium, that's going to be the moles of helium divided by the moles of helium plus the moles of neon, which this bottom term is just the total moles and total. So we could take this sort of generic expression here, and we could say that since N is equal to PV over RT, it's just a rearranged version of the ideal gas law, then we could rewrite the partial or the mole fraction of a gas as equal to whatever the partial pressure of that gas is times V over RT divided by the total pressure V over RT, where V over RT is the same in both because it's the same system, so this falls apart. And this really is just another way of equating the mole fraction to be the pressure of, should be pressure of 1 divided by the total pressure. So if we're thinking about this with this example here, another way to write this would be the mole fraction of helium is not only the literal mole fraction, how many moles of helium divided by the total moles, it can also be written as the partial pressure of helium divided by the total pressure of helium. And those things, this relationship, they're interrelatable simply because the V over RT, which is used to convert between pressure and amount, they're the same in both cases, so they cancel. So we can think about the fractions of moles or the fraction of pressure using essentially the same equation for a gas. So why is that useful? It can be really useful if you can measure the pressure of, say, a gas tank. Let's say you've got your tank or a balloon or whatever it is, and you measure that total pressure, which is easy. You just put a gauge right up on top, you measure that out, and you get the total pressure. Even if you have multiple gases in there, the total pressure doesn't care. That's just going to be a sum of the partial pressures of the individual gases. So say you've got your neon and helium in there. If you know what the mole fraction is, the ratio of those two to each other, which would be, in this case, the chi helium, then you can very simply compute what the actual partial pressure of helium is, meaning what is the pressure being exerted inside this tank just from the helium itself. So it's a really simple way to relate that. All right, so let's do an example using this tactic. So the example states that you've got a 1.5 liter bottle at 90 to C, and it contains a certain mass of hydrogen, nitrogen, and ammonia. And you want to equate or figure out what the partial pressure of each of those gases is, plus what the total pressure that would be read by the tank. So let's just draw this up. So we've got our tank. We're looking for P total. We're looking for pressure of nitrogen, pressure of hydrogen, and pressure of ammonia. And what do we know? Well, we know that we have a volume of 1.5 liters in this tank. We know that the temperature is 90.0 C, and we have a certain mass of 3 different molecules or compounds in the system, which we know that we could pretty easily convert between grams and moles of each of these things, which would give us an N. So we essentially have an N, we just haven't computed it yet. So we're going to need to utilize what expression here? Well, if we're being asked to compute the partial pressures of each of these gases, we could use the expression, you know, partial pressure of nitrogen equals chi nitrogen times the total pressure, but that would require us to know the total pressure of the system, which is one of the variables we're being asked to compute. So instead, what we could do is just write out a ideal gas law for each of the individual partial pressures, because we know that has to be true. We know that the pressure of hydrogen has to equal the number of moles of hydrogen times the gas constant times temperature divided by volume. We know that to be true. So that means we'd need to start by figuring out the moles, and we could write out this expression, the exact same expression, for each one of these gases. So pause the video, figure out the moles of each of those, and then let's compute the partial pressures of each. All right, so I have written out here the conversions to moles of each of these things. So those are written here, multiplied by the gas constant, the temperature in units Kelvin. Be careful there. Make sure you're in Kelvin, not in Celsius. That's always a tricky part. The way that you get that right every time is you make sure your units cancel. So we can do that really quick. So liters, and we're left with just atmospheres in our gas constant. So that gives us 54.6 atmospheres, which is just the pressure being exerted from hydrogen gas in that tank alone. So that's exclusive of all the other stuff. Do the same thing for nitrogen. I just left this as RT over V since it's the same as the first expression. I didn't write it out again, but the number of moles is here. Gives us 5.18. Do the same thing for ammonia. You get 2.81. So that's the first part of the question. You can see that the vast majority of the pressure inside of that tank is coming from the partial pressure of hydrogen. And we also know then that the total pressure is just a sum of the partial pressures of each of the individual constituent gases. So we could add these three things up here, and what we get is 62.6 atm. So that's what you would read on a tank gauge. If this were a cylinder, say a scuba tank, and you had attached to that a tank gauge, you would read 62.6. That would be the total pressure. That gauge can't differentiate between the three gases, but you can differentiate between the three gases if you know how much of each you put in. That's also why if you weigh out the different components of gases in a scuba tank, often it's done by mass. And so what they do is just put a normal scale, like a bathroom scale that you'd use to that you could stand on to measure your own mass, and they fill this with the different canisters of hydrogen, nitrogen, and ammonia, and they measure the resulting mass change, which would give them numbers like these, 5.5, 7.3, and 2.42, so that they would be able to compute what the individual ratios, mole fractions, or the individual partial pressures. This is important as you get into sort of Chem 108. This sort of idea is extended even further to think about the solubility of gases in liquids, specifically gases in blood, and why scuba tanks are made up with certain compositions and not others. And that has to do with this idea called the bends, which is that nitrogen is actually quite soluble in the blood. And instead of using just atmospheric gas, which is 80% nitrogen, which it forms bubbles in your blood, which can give you all sorts of pain when you're resurfacing from depth. Instead, they use helium, which doesn't have solubility in blood. And so in order to understand and do all of the right math for filling the right ratios in a scuba tank or in a diving tank, you need to have a good understanding of the ideal gas law, these laws of partial pressures, which are called Dalton's laws of partial pressures, and then ultimately in Chem 108 you'll learn about solubility. So building on all of these, there's lots of practical reasons why these things are important, not to mention thinking about things like climate change and thinking about the composition of our atmosphere as a product or sum of the individual components, pressures that comprise those. Things like CO2 that we emit anthropogenically, carbon monoxide, and a variety of other greenhouse gases. So this type of chemistry becomes really important when we think about those big scale issues.